Hello, my dear friends. I'm Shubham from Learnohub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnohub.com. So then, let's start. So students, we are going to start with your ICSE class 9 chapter number 6, study of first element, hydrogen. And actually we have started this chapter. We have gone through some concepts in the first video, that is the previous video. Now this is the second video of this chapter and we are going to continue the concepts of this chapter, right? And we are going to also see some questions so that we can get a fair idea how to solve the problems as well. Okay, how much you have understood the things, right? So without wasting much time, let's start and let's rock. So friends, now starting with the lab preparation of hydrogen. So far we have seen how to prepare hydrogen from water, okay, how to prepare hydrogen from acids, and now continuing the process of preparation of hydrogen from acids, okay. This method, the preparation of hydrogen from dilute acids, we are going to use actually, okay, or we actually use in our labs to produce hydrogen in lab, man, superb. Okay, so this is the method we use, and let's now see how we can produce hydrogen, what all things we need to take care of, how to set up the apparatus and all those things, observations, reactions, procedure, and XYZ, all those things. Okay, so starting from the very basic thing, whenever you are going to carry out an experiment to produce something, to generate something, to carry out a reaction of production of something, you first need the reactants, correct? And the reactants in this case, the lab preparation of hydrogen we are going to use are zinc granules, okay. Now I would definitely tell you why we are using granules here, zinc granules, okay. And along with zinc granules, we can either use dilute hydrochloric acid or dilute sulfuric acid. Now, whatever you want, you can use. Okay, either dilute hydrochloric acid or dilute sulfuric acid. Now, you would be able to correlate, sir. What we are actually going to do is, in the previous video, we have studied the reactions of dilute acids with metals, right? They give us chlorides or sulfates, right? Metal chlorides or metal sulfates, releasing hydrogen gas. So exactly, sir, you are using the same reaction? Yes, I'm exactly using the same reaction. Okay, now let's see how to set up the apparatus then. Okay, so in the procedure itself, I'm going to explain you what you have to take is a flask, okay, and in this flask, you need to add zinc granules, okay. Now, after adding zinc granules, you need to take a rubber cork having 2 holes in it, okay, 2 holes. So you have to place this rubber cork like this, okay. Now, in this rubber cork, okay, having 2 holes, through one hole you push inside the thistle funnel. Clear? This is called as a thistle funnel. And through the other hole you push inside a delivery tube, okay, a glass delivery tube. But yes, you should take care of one thing, not to insert this delivery tube in water as shown in the diagram, okay, not to insert. For now, just keep it in the air itself, okay. Now what we have to do is, we now had to attach the stopper to the stand and all those things, and we have to keep ready this water trough along with this inverted jar like thing, okay, inserted in the water, having an opening so that we could insert the delivery tube inside this jar, okay. Now forget about these things, don't read it right now, let's go through the process. So after doing all these things, now we are going to add dilute sulfuric acid or dilute hydrochloric acid through this thistle funnel into this flask which is having zinc granules. Understood? Now what would happen? What would happen? Try to remember the reaction. What were the products formed when the zinc was reacting with either dilute sulfuric acid or dilute hydrochloric acid, okay, and you would get the answer, or you would get an idea what would be the observation here, okay. So this was all about the procedure, right? Moving ahead to the observation, so definitely you would be able to recollect, right, that zinc, okay, before going to the I will come back to the observation in a quick minute, but let's see the reaction first. So here zinc, okay, when it is treated with a dilute hydrochloric acid, suppose I have taken dilute hydrochloric acid, okay, so it would result into zinc chloride and liberation of hydrogen gas. Fine. Or if I would take dilute sulfuric acid, no problem. Okay, our zinc would also happily react with dilute sulfuric acid. It would form zinc sulfate and release hydrogen gas. Fine. So zinc chloride and hydrogen gas here. Okay, and zinc sulfate and hydrogen gas. So here, what your observation would be, zinc, suppose if I am taking hydrochloric acid here, so zinc chloride is formed here, okay, inside, and hydrogen gas is being liberated. Okay, so from this thistle funnel, okay, we have taken one care that we are dipping the thistle funnel, okay, the end of the thistle funnel is dipped into the dilute acid whichever we are taking, and now when the reaction has started, okay, you would see small bubbles, right? You would see the effervescence, you would see the bubbles, okay, coming out from this reaction mixture, okay, and these bubbles would come to the surface and would release hydrogen gas. Okay, so hydrogen gas is released, and here zinc sulfate or zinc chloride is formed depending upon which acid we have taken, whether sulfuric acid or hydrochloric acid, any one of that. Understood? So here what you would observe is effervescence, bubbles resulting into the liberation of hydrogen gas. This would be your simple observation. Very clear? So observation you can just try to identify by looking at the reaction also. Some key observations are like hidden in the reaction itself. Clear? Now, when we are carrying out the reaction, the question which would have arisen in your mind that why we are using zinc granules. Okay, why the granules? So in zinc granules, okay, it is not pure zinc. Okay, it is having some impurities like copper, and this impurity, we actually want this impurity. Why? Because for example, like here the copper is an impurity, so the copper, what it does, it speeds up this reaction, okay, the reaction of zinc with dilute acids, so it is beneficial for us. Okay, understood. But now there comes a problem with such impurities. So one of the impurities is copper, but other impurities are also there, and because of these impurities, what would happen is we would get hydrogen gas, but that gas would be impure hydrogen gas. Okay, now let's focus on this impure hydrogen gas later. First of all, let's see how to at least collect this impure hydrogen gas. Then let's purify this impure hydrogen gas. Understood? Clear till this point now? Okay, so till this point we have seen the reaction taking place in the flask, correct? The hydrogen gas being released, though it is impure, slightly impure, but still it is released. Now it's time to collect that hydrogen gas, correct? So till this time we haven't, till this time, like we haven't dipped this delivery tube into the water. What we are going to wait for is, we are going to wait for all the air inside this flask to get expelled out. Okay, once all the air from this flask gets expelled out, okay, whatever the gas which would come out through this delivery tube would be purely hydrogen gas, correct? Initially, before the reaction would take place in this flask along with the zinc and dilute sulfuric acid, okay, means before adding dilute sulfuric acid to zinc, there was plentiful of air in this flask, correct? Now when the reaction takes place, hydrogen is getting evolved, but along with it some air is also present. Air means oxygen is also present, right? So we would wait till all the air from the flask is expelled out, so that whatever after all the air is expelled out, okay, here inside the flask everything would be hydrogen. Okay, if all the air is expelled out, then inside, okay, everything would be hydrogen because reaction is taking place. Got the point? Okay, so when the reaction takes place, okay, when it starts to react, hydrogen gases have started to get, means hydrogen gas is releasing, okay, is getting released in the flask, and we will wait till all the air in the flask is removed. Okay, now when all the air from the flask is removed, okay, what would be in the flask now? Only hydrogen gas. And now when only hydrogen gas start to comes off through this delivery tube, okay, fine, then we would put this delivery tube in this inverted glass jar, okay, now which is having this water in it. Fine. Now how we are collecting this thing? Okay, how we are collecting hydrogen gas? By downward displacement of water. Understood? Okay, so this downward displacement of water is carried out, but not downward displacement of air. Okay, so you would study in your class 10th the collection of ammonia gas, okay, or collection of hydrogen chloride gas, and there we would see upward displacement of air, downward displacement of air, and all those things. But let me explain you here first of all, okay, because maybe you would be new to this term. Okay, so here downward displacement of air means, suppose I'm collecting a gas, any gas for example, okay, and that gas is lighter than air. Okay, so if it is lighter than air, okay, what would happen is I have placed this inverted jar, gas jar, okay, or glass jar here. So since the gas is lighter than air, okay, it would move up, so it would form an upper layer, right, in this gas jar. And since more and more gas would come, okay, it would push the air outside slowly and gradually, right? Okay, so more and more air, more and more gas coming, so gas's volume would increase, and it would push the air outside. So this is called as downward displacement of air. Fine. Now suppose if the gas we are collecting is heavier than the air, okay, so then we would collect it in such way that we would place the delivery tube, okay, and we would keep the gas jar straight, not inverted. Okay, now what would happen? The gas is heavier than the air, so it would settle at the bottom. Okay, air would be above that gas, and since more and more gas would come, the level of gas would increase and the air would start to move out slowly and gradually. Okay, and in this manner the air is displaced, but now here the displacement of air is upwards, so therefore it is upward displacement of air. Now similarly in the same case, okay, here what we are doing is we are passing the gas through this water trough, okay, glass water trough, and what this gas is doing, since this gas is not soluble in water, what it does is, we all know gas is lighter than water, so it would run up, okay, like the same this case. So since it would run up, it would push the water down, so more and more gas coming in, okay, the level of water would move down and down, okay, would move lower and lower, sorry. Got the point? Clear? So what is happening to the water? Water is moving downward, so this is downward displacement of air. Understood? Okay, downward displacement of, sorry, water. Okay, and now why we are collecting the gas through the water? Okay, why downward displacement of water is carried out? Why not downward displacement of air? Since it is lighter than air, so air would get dispersed out and we would collect hydrogen gas. But the problem here is, okay, hydrogen, if it would get mixed with air, okay, it forms an explosive mixture. Why? Because air has oxygen, correct? And here hydrogen along with oxygen, okay, oxygen supports combustion, hydrogen is a combustible gas, means hydrogen is something like a fuel. If it mixes with oxygen, and if we would slightly burn something else near this apparatus, oh my god, doom, it would result into an explosion. Understood? So that's the reason we don't collect it by the downward displacement of air, because we don't want our hydrogen to get mixed with the air, because we don't want to take any risk, okay, of explosion and all those things, of burning and all those things. Fine. So that's the reason we don't use downward displacement of air method. Okay, since we don't want our hydrogen to get mixed with the air, since if it gets mixed with the air, and if suppose some burning takes place near the apparatus, it would result into the combustion. Okay, it would result into the burning. Clear with this point? Okay, now let's purify our hydrogen gas. Now whatever hydrogen gas we have collected here, it is impure, as I have told you. Here the hydrogen which is getting formed because of the impurities in the zinc granules, some trace amounts of gaseous impurities are also mixed with the hydrogen, right? And these gaseous impurities which are mixed with the hydrogen are also present in this hydrogen. Understood? Now we have to make our hydrogen pure. Okay, so what are the impurities then? Okay, so which impure gases are present? The impure gases which are present are arsine, phosphine. Okay, see these two gases. Okay, along with them, impure gases may contain oxides of nitrogen, like for example nitrogen dioxide. Okay, also it may contain hydrogen sulfide, sulfur dioxide, carbon dioxide. Okay, so phosphine, arsine, hydrogen sulfide, sulfur dioxide, carbon dioxide, nitrogen dioxide, and it may contain water vapor as well. Fine, clear? So now how to remove these gases then? Let's remove these gases one by one. Fine. So first we will remove phosphine and arsine. How we are going to remove? We are going to take that impure hydrogen, okay, and here we are going to pass this impure hydrogen into first into this. For example, I am taking a flask. The impure H2 is coming. Fine. So I am going to pass it through first silver nitrate, AgNO3. Okay, I will just write here normal silver nitrate. Okay, no need to go into the formulas and all those things. Fine. And when I would pass this impure hydrogen to the silver nitrate, okay, what would happen is this phosphine and arsine would get removed, okay, from our impure hydrogen gas, and now our hydrogen gas is free from phosphine and arsine gases. Okay, but it is only free from phosphine and arsine. Okay, still it has this much gases. Okay, let's move ahead. Then what we do is again we pass this impure hydrogen, still it is impure hydrogen gas, again into similar type of flask. Okay, here having two openings. Okay, delivery tube in the tube from which the hydrogen is coming, and now we pass this gas through lead nitrate. Fine. Now what lead nitrate does? Lead nitrate removes hydrogen sulfide. So this is also what this gas also got removed. Fine, but now still these four gases are remaining. So what we do is again we pass this impure hydrogen gas into some another here. Okay, this is the another delivery tube. So impure hydrogen gas. Okay, sorry. And now you have to take care of one thing. The delivery tube should be above the solution, whatever you are taking, right, in order to purify the hydrogen gas. So the delivery tube should be above. Fine, delivery tube should be above the solution, like this. Okay, and the tube which you are through which you are passing the impure gas into the solution should get immersed in that solution, because the gas would then get directly into the solution. Whatever impurities are would remain in the solution, and the gas which would be free from that particular gaseous impurities would get released out of that solution, and the delivery tube would carry it to the next flask. Understood? In this manner. From this also the same process. Now from this here we are passing this in order to remove this impurities, CO2, SO2 and NO2. SO2, CO2 and NO2. Okay, or CO2, SO2, NO2 means carbon dioxide, sulfur dioxide and nitrogen dioxide. In order to remove these three impurities, we pass it through the caustic potash solution. Okay, caustic potash, KOH. Fine. And lastly, okay, through like the same arrangement, okay, what we do is we pass this through a U tube. Fine, and this U tube has anhydrous calcium chloride. Fine, anhydrous calcium chloride. So this anhydrous calcium chloride's work you can just remember, or why to remember? We have studied the use of calcium chloride, right? Now you will tell me what is calcium, what would be the use of calcium chloride here. Now the things are on your screen, so you can think of something that you can think of a reason why we are using anhydrous calcium chloride here. Okay, pause the video and have a look over the screen. You definitely would get the answer. Okay, so I hope you would have used your brain, okay, and would have reached some point that The only impurity left is water vapor, right? And anhydrous calcium chloride, okay, which means that it is not associated with any water, correct? And calcium chloride is a deliquescent substance. We have studied in chapter number, I guess it's water chapter, correct? So chapter name is water, right? And in that water chapter we have studied that calcium chloride is the deliquescent substance. It would absorb the moisture, right? It would form a saturated solution and all those things. So here also calcium chloride would absorb moisture, water vapor, right, from the hydrogen gas, which is only impurity now, because see, all the impurities have been removed. Phosphine, arsine, hydrogen sulfide, all these three gases are removed. So this 6 are removed. Now only remaining is water vapor. Fine. Okay, so all of them, phosphine, arsine, hydrogen sulfide, sulfur dioxide, carbon dioxide, nitrogen dioxide, are removed. So water vapor is also now removed because calcium chloride would absorb the water vapor, okay, and make the hydrogen gas free from water vapor. So in other terms, we can say that it dries the hydrogen gas. Clear? Now you should have, means one more question you can get in your mind, that for drying the hydrogen gas, we are using anhydrous calcium chloride here. Why can't we use concentrated sulfuric acid? It is a very good drying agent, correct? It just like sucks water superbly, correct? So why we don't use sulfuric acid, concentrated sulfuric acid? Okay, but now let me tell you, we have got our pure hydrogen gas right now. Okay, woohoo, correct? So yes, here the hydrogen gas which is coming out, it is pure hydrogen gas. Okay, now coming back to the question, why we can't use concentrated sulfuric acid to dry hydrogen gas? Okay, because concentrated sulfuric acid reacts with hydrogen gas, man. Okay, now everyone is trying to like make the things much more complicated and much more difficult for us. Okay, so that's the reason here concentrated sulfuric acid is not used, because it is reacting with our hydrogen gas, and if it reacts to form water and sulfur dioxide. Now again the purpose of carrying out, or the purpose of drying the hydrogen gas would get destroyed, because through all these efforts we have got now somewhat pure hydrogen just having water vapor. And if you would again dry that hydrogen gas with the sulfuric acid, that concentrated sulfuric acid guy, then it would again turn our hydrogen gas to water and sulfur dioxide, and then again we would be in a headache that, oh, we were just this close from the pure hydrogen gas, and we again lost it. Result, because now the hydrogen gas, okay, has been reacting, means hydrogen gas, okay, it got reacted with sulfuric acid, concentrated sulfuric acid, and got converted into water and sulfur dioxide. Correct? Fine. Let's now move ahead. So that's the reason we cannot use concentrated sulfuric acid. But whatever hydrogen gas we have got now, the pure hydrogen gas, we collect it over mercury. Okay, now why mercury? Because mercury is very good, it doesn't react with hydrogen. Okay, fine. So that's the safest, so that's safe for us to collect the hydrogen. So we collect hydrogen, okay, through over the mercury. So finally we have collected hydrogen. Okay, finally let's see the precautions which we need to take while carrying out this lab preparation of hydrogen, which is very easy. We need to take care of very one important thing, that is we should not allow leakage of hydrogen gas. Okay, so because if hydrogen gas would leak out, we know in our air there is plentiful of oxygen, and it would mix with the oxygen, it would result into a mixture which would catch fire easily, right? So we need to take care of those things. Okay, and also along with avoiding the leakage, if at all some leakage is taking place, we cannot ensure 100% foolproofness, right? Okay, because some or the other where maybe it can happen that leakage may happen. So that's the reason we should also take care of one more important thing, that is if at all some leakage would take place, but we should ensure that we are not burning anything around, okay, the apparatus where we have set up, okay, burning anything around the apparatus where we are carrying out to collect the hydrogen. Okay, so that if at all there is some leakage, if we are avoiding the burning near the apparatus, then we would be avoiding the risk of hydrogen getting burnt. Clear? Okay, avoid burning near the apparatus. The another thing is we have to collect only after all the air is expelled out from the flask. Okay, collection only after all the air is expelled out of the flask. We have seen this thing, okay, while we were doing the process. And lastly, end of the thistle funnel should be dipped in acid. Why it should be dipped in acid? Because we don't want our hydrogen gas, okay, to escape through the thistle funnel. Clear? Okay, so that's it. One more interesting thing is, why not to use concentrated sulfuric acid instead of dilute sulfuric acid? Okay, why concentrated sulfuric acid is not used, okay, instead of dilute sulfuric acid? So the reason is very simple. Concentrated sulfuric acid has oxidizing properties, which simply means that what it would do is, in simple terms, now you don't know what is oxidation reduction till now, so no need to worry about that, about the oxidizing property or oxidizing nature. Okay, sulfuric acid simply, okay, it would turn, for example, I'm taking zinc and I'm using concentrated sulfuric acid, right, in this reaction, okay, instead of dilute sulfuric acid, what would happen is zinc sulfate would get formed, water would be formed, and sulfur dioxide gas would be formed. Now, looking at the reaction, can you just figure out why we are carrying out the reaction of zinc with the acids? Yes, yes, definitely you would be answering, right? To prepare hydrogen, sir. And where is the hydrogen here? The hydrogen is not there in the product. Zinc sulfate, water, sulfur dioxide gas is there, but no hydrogen. So then why would we carry the reaction? That's the reason we don't use concentrated sulfuric acid. Very easy, because it also again does the same thing like the dilute nitric acid. Okay, it gives us water, not hydrogen. Fine. Okay, so it is also giving us water, just the same like the dilute nitric acid. Okay, clear? Okay, now moving on to the third method of preparation of hydrogen. Very simple. Now you don't be scared of, because you would be thinking, sir, the first method was from water, it was so long. The second method was from acids, it was also too long. But don't worry. Okay, the third method is quite small. That is, we are just going to simply prepare hydrogen by using alkalis. And now here we are going to react our alkalis like sodium hydroxide or potassium hydroxide. Okay, now we know this is called as caustic soda, this is called as caustic potash, so we call them as caustic alkalis. Okay, so these sodium hydroxide and potassium hydroxide we are going to treat with only 3 metals. Okay, and these 3 metals are very special. Okay, you could realize them. Okay, which are zinc, aluminium, lead. Man, you would be thinking, sir, this zinc and aluminium and also lead were reacting with acids, right? You can just correlate, you can just remember a few slides, means like you can just remember that we have studied the reaction of the metals with dilute acids, okay, in the previous video, and you would be surprised to know that they reacted even with acids. They are reacting even with the alkalis, which means bases. Okay, so since these metals are reacting with both acids and alkalis, okay, they also react with acids, they are also reacting with alkalis. Okay, so they are special in nature. Okay, so we call such nature as amphoteric nature, the nature in which our metals are reacting with both alkalis as well as acids, or both bases as well as acids. Okay, so we call these metals, that's why we call them as amphoteric in nature. Fine, very clear. Now let's see the reaction with the alkalis. Very simple reactions are there. So here zinc, okay, these metals, they react with hot concentrated alkalis. Okay, so here hot concentrated, okay, NaOH or KOH. So reaction of zinc with NaOH, zinc with KOH. Very simple. Same way reaction of lead with NaOH, lead with KOH. Okay, now see what they give us is they have the amphoteric nature, okay, and they react with this hot concentrated, okay, alkalis NaOH and KOH to give soluble salt and hydrogen gas. What we always want is hydrogen gas, right, in these reactions. So soluble salt and hydrogen gas. And now which soluble salt is formed here? So in case of zinc and sodium hydroxide or caustic soda, okay, hot concentrated sodium hydroxide, we get sodium zincate, Na2ZnO2 and hydrogen gas. Here we get Na2, okay, sorry, K2, I'm sorry, here it would be K2ZnO2 and hydrogen gas would be released. Okay, so Na2ZnO2 and hydrogen gas. And then for zinc and potassium hydroxide, it is K2ZnO2 and hydrogen gas. And this Na2ZnO2 is called as sodium zincate. And K2ZnO2 is called as potassium zincate. Fine. Clear? Now, in the same way, lead reacts with sodium hydroxide and it forms sodium plumbate, Na2PbO2, okay, plus hydrogen gas is released, and lead reacts with potassium hydroxide and forms K2PbO2, okay, sodium plumbite and potassium plumbite. Along with the liberation of hydrogen gas. Clear? Okay, so zinc and lead reacting with hot concentrated NaOH and KOH exactly in the similar manner. Okay, zinc reacting with NaOH to form Na2ZnO2 and hydrogen. Zinc reacting with KOH to form K2ZnO2 and hydrogen. Same way, lead reacting with NaOH to form Na2PbO2 and hydrogen. Lead reacting with KOH to form K2PbO2 and hydrogen. Okay, the similar type of reactions. In the same manner, aluminium also reacts. Okay, but here the reaction of aluminium with NaOH involves water and it forms slightly different type of product. Okay, the product is also a soluble salt, no doubt. The product is soluble salt and hydrogen gas, but the soluble salt is like something different formula. It is having some slightly different formula than the zinc and the lead products. Okay, it is NaAlO2 or KAlO2. Okay, and hydrogen gas is released. Okay, so this would be the reaction. Al plus KOH plus water giving KAlO2 plus hydrogen gas. Okay, and all these reactions you need to balance out. Okay, some reactions won't, means all these reactions you need to take care to balance them. Okay, this also fine. So aluminium along with sodium hydroxide or potassium hydroxide and water would be another reactant here. Okay, important reactant, and then they would react. Okay, fine. Okay, so aluminium along with sodium hydroxide and water, aluminium along with potassium hydroxide and water, okay, to form this NaAlO2 and hydrogen gas and KAlO2 and hydrogen gas. Now this NaAlO2 is called as sodium metaaluminate and KAlO2 is called as potassium metaaluminate. Okay, I'm just writing one name, sodium metaaluminate, and here potassium and the same metaaluminate. Clear? Okay, now coming to the last concept of this chapter, which is oxidation and reduction reactions. So we will understand one by one both of them. First, let's see what are oxidation reactions, and now we are here going to understand, okay, these oxidation reactions in terms of oxygen and hydrogen. Okay, in terms of addition or removal of oxygen and hydrogen. Okay, so you just try to understand that we are going to understand the oxidation reaction in terms of oxygen and hydrogen. Fine. So oxidation, we can say that if in a reaction you are observing addition of oxygen, okay, in a reactant, okay, addition of oxygen in a reactant, then it is an oxidation reaction. Or if you are observing removal of hydrogen, okay, from the reactant in a reaction, then you can say that the reaction is oxidation reaction. Okay, let's quickly see the examples, then you would get what I'm telling to you. See, if I treat carbon with oxygen, okay, suppose I'm burning carbon in presence of oxygen, I know I would get carbon dioxide. So in this reaction, you can see here, oxygen is getting added to the carbon, and carbon, after addition of oxygen into it, is getting converted into carbon dioxide. So here oxygen is getting added to carbon, therefore this is an example of oxidation reaction. Now see, oxygen is getting added to carbon, therefore we say that carbon is getting oxidized, right? Addition of oxygen in carbon, so oxidized. Understood? So carbon here is oxidized to carbon dioxide. Clear? Since, so in whichever reactant the oxygen is getting added, we say that it is oxidized. So here oxygen is added in carbon, so we are saying that it is oxidized to carbon dioxide. Clear? Okay, oxygen is getting added to the carbon. Clear? So we are saying that it is getting oxidized to carbon dioxide. In the same manner, if you would say removal of hydrogen, so here for example I am taking this reaction, hydrogen sulfide and chlorine gas, simple reaction. Okay, it results into hydrogen chloride, means HCl, and sulfur. Okay, so hydrogen sulfide and chlorine. Okay, so 2H, 2 chlorine, 1 sulfur, 2H, 2 chlorine, 1 sulfur, so it's balanced. Okay, now what is happening here is, see, the hydrogen is getting removed from the hydrogen sulfide, and after the removal of hydrogen from the hydrogen sulfide, what is remaining? Sulfur, which is given as the product. Okay, so here we can say that removal of hydrogen is taking place. Okay, so this is the example of oxidation, because removal of hydrogen is oxidation. So in a reaction, if you observe removal of hydrogen, then it is oxidation reaction. Clear? Now here, from which reactant the hydrogen is removed? From hydrogen sulfide. Correct? So hydrogen sulfide is getting reduced. Correct? Sorry, oxidized. Sorry. So from the reactant, okay, if from a reactant hydrogen is getting removed, removal of hydrogen, then it is getting oxidized. Understood? The same logic, exactly the same logic. If you observe removal of hydrogen from the reactant, oxidation reaction, the reactant from which the removal of hydrogen is observed, okay, that reactant is getting oxidized, okay, and it is getting oxidized into the resultant product. Okay, so resultant product is simply sulfur. Hydrogen sulfide is getting converted into sulfur. Okay, so we can say that hydrogen sulfide is oxidized to sulfur. Clear? Okay, now what are reduction reaction then? Okay, exactly the opposite of oxidation you need to remember in the same way. Okay, now let me give you a trick here. See, oxidation, O, so addition of O. Understood? Oxidation's O, therefore addition of O. Okay, now what would be reduction? Addition of then H, right? Since oxidation is addition of O, reduction would be addition of H, correct? So reduction is addition of H, and then reduction would be removal of, okay, since here there is H, here would be O. Understood? Simply the simple trick. Now whenever you observe addition of hydrogen in a reaction, that is a reduction reaction. For example, suppose I am taking ammonia, okay, and I am adding and I am treating it with chlorine. Fine. So I get here nitrogen and HCl. Okay, so what here is happening, you can observe here, the hydrogen is getting added to the chlorine, correct? And after addition of hydrogen to the chlorine, it is getting converted into HCl. Fine, you can observe this. So since here the addition of hydrogen is taking place to form HCl, okay, therefore it is a reduction reaction. Now in which reactant the addition of hydrogen is taking place? In chlorine. So we can say it is getting reduced, and it is getting reduced to what? To the product which it is forming. Okay, to the product which it is getting converted. It is getting reduced to HCl. Clear? Okay. Now in the same manner, removal of oxygen, very simple. So if I am taking this copper oxide and I am treating it with hydrogen, okay, what you would observe here is the oxygen would get removed from the copper oxide. Okay, so what would remain then? Only copper, and this hydrogen would pick up this oxygen and form water. In this way you can observe, in this way you can remember. See, so here oxygen is getting removed, okay, to form copper. Okay, so oxygen from the copper 2 oxide. Okay, this is the copper 2 oxide, or you can say it is cupric oxide. Okay, because copper 2 plus radical is of cupric. Okay, in this copper 2 oxide, here Cu2 plus and O2 minus, these are the radicals. Okay, so cupric, because Cu2 plus oxide. Okay, so from this cupric oxide, oxygen is removed and it is resulting into the formation of copper. Clear? From this cupric oxide, Cu2 plus and O2 minus. Okay, this cupric oxide, oxygen is removed, resulting into the formation of copper. So removal of oxygen means reduction. So this means that our copper 2 oxide is getting reduced, and it is getting reduced to copper. Okay, so removal of oxygen is taking place here. Fine, resulting into copper. Okay, so reduction of copper 2 oxide into copper is taking place here. Got the point? What is oxidation? What is reduction? Okay, so let's end this video with a very interesting question. So question is on your screen. You can pause the video and try to answer the question on your own. Try to think. Okay, if you would think enough efficiently, you would definitely get the answer. Okay, I hope you would have applied your brains. Okay, now let's see the answer. So is the below given reaction example of oxidation or reduction reaction, or both? Okay, so the reaction is this: Cl2 plus H2S giving us 2HCl and sulfur. Fine. So now, some moment ago only we have seen this reaction as an example. You can observe here, okay, the hydrogen is getting added to chlorine, resulting to the formation of HCl, right? Hydrogen adding to chlorine, correct? So resulting to formation of HCl. So addition of hydrogen is observed here. Addition of hydrogen means reduction, right? So reduction is observed here. So we can say that this is a reduction reaction. Fine. But wait a minute. Take a pause. You can see here the hydrogen, okay, from hydrogen sulfide, okay, it is getting removed. Fine. The hydrogen is getting removed from the hydrogen sulfide and resulting into the formation of sulfur. Oh, right? Hydrogen is getting removed from hydrogen sulfide, okay, resulting into the formation of simply sulfur. Okay, if this is gone, only sulfur is remaining. So here sulfur is remaining. So here there is removal of hydrogen taking place in this reaction. And what is removal of hydrogen then? Addition of oxygen is oxidation, correct? So removal of hydrogen is also oxidation, right? I have told you, addition of oxygen, oxidation, right? Then removal of, your oxygen is done, so then hydrogen would be there. Okay, in this way we have discussed, okay, addition of oxygen, oxidation, and oxidation is also removal of, here oxygen is used, then hydrogen, and here hydrogen is removed, okay, to form sulfur. So this is an example of also oxidation reaction, right? Hydrogen is removed to form sulfur. Clear here? Okay, so removal of hydrogen, oxidation. So it is also an example of oxidation reaction. So yes, it is an example of both reduction as well as oxidation reaction. And it's not in your syllabus, but let me give you a glimpse that such reactions, okay, which are in which we can observe both reduction as well as oxidation, are called as very, very interesting type of reactions, which are called as redox reactions. Okay, nothing more about it right now, okay, because it's not in your syllabus right now. So just let's end up with this thing. So friends, with this we have reached the end of this video, and I hope you would have enjoyed learning with me. You would have understood the concepts which we have learned so far. But you can comment in the comment section and tell me, okay, I would be glad to know that you understood or you enjoyed learning with me. And as you all know, Learnohub matlab free hai par best hai. So see you in the next video with the concepts of next chapter. Till then, keep studying. Bye bye and have a great day.